Okay, this is a topic that is a bit tricky, but might be worthwhile. Okay, so transformations of functions by means of compositions. So rather not functions, but rather of graphs of functions. So functions are not graphs, graphs are not functions, but graphs are visualizations of functions. So the question becomes, what happens to the graph of a given function if we compose it with another one? So that's an example, just a starting point is on the left. So we know the graph of the function, which may or may not be parabola, but it looks like one. And then we compose over there the second line with another function. So technically what we're looking at here is certainly a simple function to think about, but this is what literally happens. X is the input. This is my function f, unspecified, and then multiply by 3. That's the next function, whatever that is. So this is y, and this might be z. Okay, so that creates certainly a new function from x to z on the z axis, and then we ask ourselves what the graph is of the new function. So it's a very effective way of reducing the number of functions that we have to worry about. If this is a parabola, then we can see what the most elementary transformations of most elementary functions to compose with. What would they produce? What do they do to the graph? So the transformation that we have used have been primarily shift, flip, and stretch. Okay, so and these are the ones we'll be looking at. So think about what's going to happen to a parabola. But we're going to let's review first. So review what functions do to the x-axis, or to a real line. The real line, so it could be x-axis, it could be the y-axis. That's the thing about it. The function, if we do a composition of function with another function, that another function might come before, it might come after the function. The effect is very different. Okay, so that's why I don't specify what that function, the other function, does to which axis. It could be x-axis or y-axis. But primarily it is, let's call it, say, g of x. Okay, if it is the x-axis, and the three categories are hold on a second, x. No, I don't want to of x. My function f is of x, so let me use the difference. Say g x is equal to g of t, or z is equal to g h of y. Okay, so y equal f of x, and then we will compose it with a g beforehand, before f, or with z after. Okay, so x, y, t, x, y, z. This is my f, and we insert either g prior or we insert h after. Okay, so this is what we will be doing. But that's not. I just want to have it here so we know why we're doing it. But the review of what a function does to a real line is so that's a real line which may be x or y axis, and then well, let's say it is the x axis. Okay, then no, let's take it y axis. Y axis. Okay, so 3y is a stretch. Z is equal to y plus 3 is a shift. And z equal negative y is a flip. Okay? So stretch. So if it was distributed uniformly, then the result is still distributed uniformly, but the distances have tripled. The shift is the distances remain the same, but the zero is elsewhere now. Okay, that's the shift. And flip, everything just it's as if the positive direction points in the opposite direction. Okay, so these are the three functions, and then as I said last time, our interest is what happens to the graph of y equal f of x, and which lies on the x-axis, on the xy plane, and which means that what we're interested in is in the transformations of the xy plane. So our interest is, once again, transformations of the xy plane. And by that I mean I want you to see the contrast with what just came up, and that is the transformation of the real line. So we have been doing in this previously, and this is a review of a transformation of the real line. Or of x-axis. You transform the x-axis, okay, we know how. Those are the three main operations. You can transform the y-axis, once again, three main operations. Combined together, they will produce a transformation of the xy plane. It is, if you just look at the description, it is very feasible because so suppose if I stretch the x-axis, then the idea is in the x-axis that lies on the xy plane. Okay, then what's going to happen is you should think about as if there are many x-axes like this, and all of them get stretched or flipped or whatever. Okay, so whatever happens to the whatever's happening on the x-axis is happening to every other line parallel to the x-axis. Okay? And in the same manner. To demonstrate that, we can just look at the coordinates. That's the why we care about the coordinate system. So let's pick a transformation in that order. In fact, probably let me change the order. The first one is the shift, the second one is the flip, and the third one is the stretch. So number one, we start with a shift along the y-axis. Let's start with that. So in other words, we are going to be shifting everything in the positive direction along the y-axis. Okay, so it is really uncomplicated if you think in terms of coordinates. So shift by 2. Okay, so every point on the xy plane lands elsewhere. Shift along the y-axis, in other words, vertically up by 2 units. So so if my original point is xy, where will it end up? Shift everything up by 2 units.
X and y plus 2.
That's right. X, y plus 2. Okay, so if this is xy, as I have here, this will be x, y plus 2. Well, let me make a bigger picture. xy, and this is x, y plus 2. As you can see, the changes with respect to y only. As you can see, this is what we're going to be doing for a few minutes. So I set that whole business about functions z equal f of xy aside, and I will be thinking, or we will be talking about transforming the xy plane, and whatever is on the xy plane will be also transformed. Okay, so if it happens to be the graph, great. but you can transform anything you want. Okay, so to illustrate this with something more specific, XY plane. So this is my XY plane. I can certainly. So this is the XY plane. It has axes. It has the grid, and whoops. 1, 2, 3, -1, -2, 1, 0, 2, -1, -2. Okay, so it is uncomplicated really to think about what we're trying to do here. I paste, okay, and then that's what so I put it back where it was originally at first. Okay, so that's like I have 2 pieces of paper. One of them is transparent on top of the old, and now I will keep the bottom one just for reference, and then see what happens. Okay, so this would be the shift, right? The shift by 2 units. Okay, the whole thing is shifting. You can see what has happened to. I'm not sure how clear it is. But you can see what happens to the x-axis. The x-axis, look at the x-axis ended up 2 units up. Nothing else has changed. For example, the y-axis has shifted, but it did not change its location because it's infinite. The shift leave it intact, and so every line parallel to the y-axis will behave this way. Okay, so that's one illustration, and now let me have another one here, just in case. You can always do the same with such application as paint. Okay, so I could draw anything on it, and then okay. No. Okay, I draw something on it, and then I can once again examine what is happening to the XY plane in the same manner I just showed you. Okay, transparent. So once again, you start in the same position, and then you shift it up, or you shift it down. Okay. You can also shift it left and right. Okay. What else can I do? Well, we're not going to be turning. So that's in a different class. Turning, certainly very interesting operation. How you can rotate an object, a plane around the center. You need a lot of trigonometry there, by the way. No, we'll be doing only things are either relative to x or relative to y. Only the two. So those 3 operations that we have had will be applied to these 3. Those 3 operations will be applied to the 2 axes, and therefore there will be total 6. Okay, so I just did 2. The shift, vertical shift, the flip. Let me show you the flip. Right. So I took this, I flipped it, and then I could put it back on just for reference to see what has happened. Right. It is upside down. Okay, well, before, let me, we know what happens under the, we know how to implement the shift. That formula that we're looking at in the middle, so let me write it down. So shift by k is given by xy goes to x y plus k. When k is negative, you were moving down. Okay? The second one is the flip. That, as you can see, if you look carefully, you can, what is the more precise description of the flip? More precise, I mean, about a flip about what? Take calculators, computers, cell phones, please take them outside. So we did a flip previously. We did a flip over here, step number 2, or transformation number 2. The flip was, where is it? Over here. It was about the origin. Okay. Now we are not dealing with a line anymore. We're dealing with a plane. So how would you describe the flip? A flip about what? Once again, this is the x-axis, right? So the x-axis is the horizontal one, and we do this. Okay, the x-axis remains intact. So look at it. Okay, so I flipped it, flip the result, and then to put it back on, I'll make sure that x-axis is aligned. Okay. What is the formula? Where does xy go? Well, the x-axis. Let me. So that picture does not have a grid on it, but this one does. So let me. Okay. Copy and paste. Okay. I'm not sure if I have a flip here. There is a rotate here. Okay. So I flip it like this. Okay, that doesn't look right. What happened here? My drawing was poor, so when I flipped it, it's off. Is it really that bad? Those lines are not very vertical. Okay, so so let me try it this way. Let me go back here, and let me have one point. In addition to all the complex picture, I'll have one point over here, over here. No, over here. No, and I call it xy. Okay, and now I'll do a flip again. Okay. Okay, so I'm doing the flip again. So it's you can see that I flip vertical. Okay. So okay, can you tell what has happened to the point xy? If you can see it.
Y becomes negative.
Right. And nothing happens to x because the transformation is entirely vertical. So nothing happens to the x coordinate. Okay, so it goes to x negative y. Okay, number 3 still. So the 3 will vertical transformations. Okay, so the third one is so this is number 1, number 2, and number 3 is the stretch. Stretch. So stretch. I didn't say it in the first one. Stretch by k vertically, and this is stretch by say k also vertically. So there's a k being the coefficient, that ratio of transformation that we did with the x-axis, but this time once again, as I said, every vertical line is stretched, and so once again, if let me go back okay, so that's the original one, and I'll stretch it. There is an operation. So let me try to double it. Well, it doesn't really matter what the exact number is. Okay, here it is. I'm stretching. Okay, I'm stretching, and it is stretched. Now I try to place it the same spot, primarily keeping the x-axis intact. y-axis also is intact. The stretch is visible, right? So that blue curve produced a new blue curve, and you can see once again what has happened to that point x, which is the generic point xy. What's happened to it? It has moved. Which way it moved? It moves vertically again. So once again, there won't be anything happening to the x-axis. Okay, so well, you can probably guess what the formula is. Xy goes where? X, ky, right. Okay, so k, if k is 1/2, it will be shrink, obviously. Like I said, whatever we have learned about transforming an axis will be still applicable. Okay, so that's what's happening vertically, and now I don't have to do a lot of work and just and think about what happens under horizontal. It's exactly the same. So I just take it and copy and just change vertical to horizontal. Okay, well, and so once again, as I was saying, I will switch vertical to horizontal. What difference does it make as far as the algebra is concerned? X and Y are flipped in the sense that if in the first column on the left nothing was happening to X, something was happening to Y because we were doing transformation along the Y-axis. Okay, this time Y-axis. This time it's going to be along the X-axis. Okay, so it's a horizontal shift. So the formula becomes what for the shift, horizontal shift? What's the formula?
X plus k,
comma y, right? X plus k, comma y. Okay. The flip is about what?
Negative xy.
Yes, but I would let me do that. Negative xy. But the description, the flip about the y-axis, right? So let me do that so that we have that available. Okay, so, oops, that's not the right one. So let me just do the other flip. So I flip it about the y-axis this time. So it is a flip horizontal, right? So x has changed, so the flip is horizontal. Okay, so you can see how it has flipped. You can see where my xy ended up. So if I realign my x's, I can see where xy ended up. So it was on to the right of the x-axis, became to the left of y-axis. Vice versa too. Remember that what multiplication by -1 does, positive becomes negative, -5 becomes positive. So it jumps. So if it jumps around the origin on the x-axis, then it jumps across the x-axis whenever we are dealing with we have a plane. Okay, so once again, if you want to illustrate flip, and that's your x-axis, what happens to number x here? It jumps like this, or it jumps like that. That's the flip, literally. And then we just have the same picture, but for the plane. And so the point would be from here, it will jump across the x-axis, not across the origin anymore, but across the y-axis along the x-axis like this. So it jumps on the other side of the y-axis. That's what a flip about the y-axis is. So a piece of paper, rotated like this, especially if it is like a transparent piece of plastic with something drawn on it. That's the way to think about it. Okay, so you can see it here. And finally, the stretch horizontally. Okay, so you can guess what the formula is.
kx, y.
Kx, y. Okay, So these are the 6 transformations of the plane. You can combine and should combine them because as I said, we will be looking at what happens to the function, whether the function applies before or after. So these are the two situations that we are looking at separately. One is this, f preceded by transformation of the x-axis. That's what I have circled is f is our object of analysis, and then there's a function g that precedes x. That's the first operation there. G is the transformation of the x-axis. And then the second one is that the y-axis is changing. Okay, so as you can see, y from y to z, that's a vertical transformation. So this is vertical, and this is a horizontal. Okay, so and then it both can happen. As an example, just to get ahead a little bit, if we once again have our parabola, and then you could end up, and then so that's the parabola, the simplest parabola that you can imagine, y equal x squared. And then the question might be, what if elsewhere I'm seeing something like this? You can already guess what has happened. What's happened to, or what has happened? You can imagine you have to connect the two and realize that it is actually the same parabola, except we have done something to it. So we took that blue parabola and somehow transformed it into the orange one. Can you describe what has happened? It shrunk. As you can see, it is thinner. Okay, what else? And it was shifted both vertically and horizontally. In fact, the tricky question would be you said it was shrunk. Are you sure it was not stretched? Is it stretched vertically or shrunk horizontally? What? Why not stretch vertically? They are infinite after all. I could make it as long as I want. So which one is it? What?
Stretch horizontally.
Stretch horizontally? This way, stretch.
Yeah.
Stretch vertically. Why not shrunk horizontally?
Since light is getting narrower.
It's a trick question.
Yeah.
The trick question is that there is no answer. It could be either way. You don't know. Just let me demonstrate that it is indeed it looks similar. It looks similar if whether you stretch vertically or shrink horizontally. You can probably think of any picture of. Let me see. Okay, stretch it. Okay, so if you shrink something that is infinite and you stretch it vertically, or you shrink it horizontally, it will produce the same result. Certainly, you can start with something like a parabola in order to make that point. And I'm not saying that it is exactly the same. It is actually different, but okay. So I'll take this and do. Okay, so I'll stretch horizontally first, and then, okay, so I'll stretch horizontally. Oops. No. Stretch horizontally. Okay. Or I'll shrink, stretch horizontally. Hold on a second. Stretch horizontally. Shrink vertically. Okay. Shrink vertically. Okay. So, and now I take the same thing, and now I shrink vertically. Okay, well, so I just need to shrink more. the tricky, why is it tricky? Because we're dealing with an infinite object, and so that's why we can say that there is some, as you can see, that's the analogy. At least they more or less match here, at least hypothetically, when you have something drawn, you can see that you can make them match more or less, and you certainly can match them if you are dealing with parabolas. So once again, what has happened here is this one is vertical, no, horizontal shrinking, and this is vertical, no, horizontal stretching. Stretch, and this is vertical shrink. Okay, and as I showed you, they match at least loosely. To show that algebraically it definitely can work out, here's an example: y equal 2x, x squared, which is our parabola, original parabola, and then I will look at two other parabolas. Do I substitute before or after? Remember, that's the difference between vertical and horizontal. So vertically, y is equal to, say, how about 4x? 4x squared. Vertically, what has happened is we vertically stretched. Okay, so we took y equal 4x squared, y equal x squared, and stretched it vertically. Okay, what if we horizontally shrink? And I want to have the same thing. So I want you to see that. Let me put a z here, so there would be no confusion. So from y equal x squared, we have transformed our function into a new function that is now a function with the output of z, and z is equal to 4y. Okay, so y equal x squared, z equal to 4y. Take the composition, we end up with z equal 4x squared, right? Okay, multiplication by 4. That's two compositions in a row. So the end result is equal 4x squared. Okay, so now what do I do in order to get the same function, but with a horizontal transformation? What? For y? Say it again. I don't really want to say shrunk or anything. I just want to transform. I want to transform x. So as you can see, I have transformed. So let's start over. I have transformed z here. Okay, I'm sorry, y into z, and that created a stretched, vertically stretched parabola. So that's step number one. Is this? We ended up with a stretched parabola. So if we start here, and then we stretched it, so it has become this one, slimmer, taller. Not taller. They are all infinitely tall, so it cannot be taller. It's just, but it is slimmer. Okay. Now, what I want to do is that. So that was a vertical transformation, a stretch, vertical stretch. Okay. Now I want to have the same shape built from the same source. So this is the source, right? Y equal x squared. I want to start with the same source, but now I want to do a horizontal transformation to end up with the same curve. This is x and z. So what is the opposite? We just talked about it. The opposite of stretching vertical is shrinking horizontal. Okay, so we might be able to carry that out, but how exactly? So I'll have the same shape, roughly. So once again, slimmer. So you can slim by growing, or you can slim by thinning. Okay, so that's what I will try to carry out. So take my original parabola, which is kind of wide, and I shrink it. Well, yeah, so we're shrinking horizontally. We stretch vertically, and now we want to shrink horizontally. Indeed, we just have to come up with a formula, that's all. Right, so it is possible. It is possible. We did it with this picture, so it is possible to stretch horizontally and vertically the opposite effect, so we can do it. We can produce a new shape of this curve. These are exactly the same shape from the same exact source, but two different transformations. One is vertical, one is horizontal. Okay, so vertically, we simply multiply by 4. How do I get the same thing, but vertically, but horizontally, I'm sorry.
Wouldn't that be 4 divided by x squared?
No, if you start dividing, you're going to get, hyperbolas. I mean, you have division by 0. So the transformation that we are after is the same. I think you just, you don't divide by x, or maybe I just misheard you. What was the?
Times by fraction.
Right. Well, but remember that I want to have the formula the same. Well, let's check out. So what was the suggestion?
I said 4 divided by x squared.
I think you're sure it's not x squared divided by 4. That would make sense. For 1, it would be a parabola. X squared divided by 4 will be a parabola. So in that sense, that is a step in the right direction. You also, because you divide by 4, you expect a shrinking of the graph. The problem is x squared divided by 4. The way I wrote it and the way you may have said it, x squared divided by 4. What kind of transformation is that? X squared divided by 4. What has happened to x squared? Well, we have 4x squared at the top, and we have x squared divided by 4, which is so 1/4 x squared. What kind of transformation is this? Yep.
The vertical shrink.
It is a vertical shrink, yes. So that's not what we want. A vertical shrink is not what we want, because we already have a vertical stretch. So we want to accomplish the same result, but with something that is horizontal, and apparently it has to be a shrinking, but it has to be vertical, not horizontal. Okay? So what is the difference if you do horizontal? It means that you are not changing y. As at the top line, I'm changing y over there. So I want to change x. To do horizontal transformation, I'm changing x. How do I change x? Yes?
Going to divide c by 4 instead.
That is another possibility. Okay, so another y. I think that's what's being suggested. Is this what you're suggesting? Well, well, let's examine it anyway. So it is. First of all, it is a transformation of x, right? It is a transformation of x because the function x squared comes after. And that is why the end result would be horizontal transformation. Okay, that's fine. But unfortunately, it's not going to produce the correct result because if you try to match it up with the formula above, it is, well, look at this. Right? Let me simplify. It will be 1/16 x squared. So what's happened to the graph? It is again a vertical shrink, right? Both of these are vertical shrinks. So multiplication by 4, division by 4, or if you divide x by 4, it will have the same effect as dividing y by 16, right? That's what I'm saying here, right? So and that's the result is not what we want. We want to go in the opposite direction. Okay, so So this is what we could try is y equal what? Something squared. So I'm changing x. That is why I keep the y squared intact. I'm not going to do anything after that, but I'm doing something before that. So instead of 1/4 x all 4, what do I do? Well, I mean, if division actually shrinks the graph, if you want to stretch, it shrinks. It is vertically shrinks. If you want to go in the opposite direction, how about multiply? This is the idea. So that is the same. So I end up multiplying by 2. So that's the tricky part. That is to whenever you do horizontal transformations, everything is exactly opposite of what you think it should be. So instead of to shrink the graph, you don't divide, you multiply. Okay, so you see how it works out. I multiply x by 2, and the result, the graph is slimmer because look at it. It's 4x squared. Naturally, it is slimmer and taller, or slimmer graph. And it is understandable because if I replace x with 2x, it means that x grows faster. And therefore, the growth of the function is faster. And therefore, that's what makes it slimmer. Okay? So the vertical one, I hope the first line was somewhat transparent. Because we carry out the function first, and then we stretch or shrink the z-axis or the y-axis, and then the formula is we just do to y whatever we want to happen to the graph. So that applies to shrinking, stretching, flipping, and shifting. Okay. So and it is works out exactly as we would expect based on this analysis on the left. On the right, it will be more complicated. So, but let's just look at the vertical transformations first and just list them so that at least we'll put that behind us. Okay. So so this is roughly how it works. So I started with a stretch, but it's really better done with a shift. So once again, in those 3 items. So so suppose the graph of, say, h of x is the graph of y equal f of x stretched, shifted k units up. Okay, then we have a formula for h. H of x is equal to, as you'd expect, f of x plus k. Okay, very straightforward. And vice versa, naturally. By vice versa, what I mean is if you start with the formula, then you know what its graph look like. Works both ways. Algebra corresponds to geometry. Okay, so we change the formula, edit k, any number k, you know what's going to happen to the graph. Or you see 2 graphs are related to each other, identical graphs, different locations, you know what has happened, you edit a number. So this is what I'm talking about. It doesn't have to be a parabola. Any kind of shape can be shifted up or down by a number of units. Okay. Number two. Let's do the flip. Let's do the flip. So I'll just take this with me. Okay. So what do I need to change? Okay. So three. Wait a minute. What happened? What am I suppose? Why I lost my suppose? Okay. Okay. I'm gonna, so three properties, and there is certain repetition there, so that's why I'm doing some copying. Okay. Okay, so that is the shift. Number one is the shift. Okay. Number two is the flip. Okay, so let's see. Suppose the graph of h of x is the graph of y equal f of x, flipped. Flipped which way? Remember? Flipped. What kind of flip is we've been talking about? Yes, flipped vertically or vertically. If you want to be specific, flip about the x-axis. Then the algebra that has been produced as a result is the negative sign in front of it. That's all. Okay. Okay. So once again, that's a flip. So once again, recognizing new functions right away. Negative x squared, you know what the graph of it is. You just have your parabola upside down. Okay, number three, it is, what's number three? A stretch. So a stretch, k by factor of k, vertically, still vertically. Then that k appears simply as a multiple, right, like this. So slimmer, which includes, well, I think one is slimmer than the other. So the height does not matter. Only the thickness is what we are able to compare. Stretched. Okay, so these are the three rules. Okay, thank you.